Well, this example has us trying to determine the reactions of a frame. And first of all, we know it's a frame because we have an internal loading. All members are pin-ended or pin connected between them, but the internal loading creates forces that are different than that of a truss, where we're only allowed to have the load at the joints themselves. Our first step in determining the reactions would be, as always, to draw a free body diagram for this structure. So to do that, we'll simply draw out our members themselves without our supports. And then place our reactions at our support locations. So we know that we have, at location A, we have a pin connection, so we have a reaction force RAX and a vertical reaction force RAY. We also, at location B, have a pin, so we should place a horizontal reaction force RBX and a vertical reaction force RBY. Our internal loadings are in the form of a moment, a point source of moment applied at a location, and this moment is 60 kilonewton meters, and that location is simply 2 meters away from location A. Oh, and I already made a mistake. This is really not location B, this is location C, and this is location B. And if we are 2 meters over and 2 meters over, we are 3 meters down. So this forms a 3, 4, 5 triangle that we can use later in our analysis. So if that's 3 meters, that means that the slope of this triangle itself, or of this line, it goes down 3 for every 4 horizontal. That means the hypotenuse has a length of 5. Now we can assess this particular free body diagram to see our ideal path for solving this problem. First off, if we count the number of reactions, and we can see that that's equal to 4 reactions. So that's 4 unknowns. And now we have 3 equations of equilibrium. We have the global sum of forces in X is equal to 0, global sum of forces in Y is equal to 0, and global sum of moments about any point on the XY plane about the Z-axis is equal to 0. This means that since we have 4 reactions and only 3 equations, that we can't directly solve for the values of RAX, RAY, RBX, and RBY without first going into our frame and taking a section cut at the joint B. This frame is determinate. That means that we can certainly solve for these forces. But we first have to look at internal forces at that joint B location. So to do that, let's consider taking a cut through joint B here. So we'll cut at location AA. This is going to be our cut location. And we'll take the sections on either side of that cut and put them in equilibrium. So we'll start with, we're going to cut at AA. And then we'll draw a free body diagram. We'll draw a free body diagram for member AB. And that will allow us to begin to solve for some of our unknowns. So remember, AB was 4 meters long. in the middle of it, it had this 60 kilonewton meter moment, and we had some forces that we don't know. We had our support reactions, R, A, Y, R, A, X, and now we've exposed some member forces at B. So we have BY and BX. Now recall that at the location of an internal pin, we have two member forces, X and Y forces. If it was a fully rigid joint, then we would also have a moment, but the pin releases that moment. And I suppose we should add our dimensions to this. We are at 2 meters and 2 meters. So at this point we can go ahead and try and solve what we can. We'll see here that we still have 4 unknowns, so, and only 3 equations. So 4 unknowns and 3 equations. Now this means that we won't be able to solve everything, but we can solve for some of it. So first let's take the sum of moments about location A and set that equal to 0. If we do so, we'll see that we have 60 kilonewton meters acting counterclockwise, so that's a positive value, plus BY times 4 meters, also acting counterclockwise as we've drawn it, is equal to 0. And now we can solve for BY is equal to minus 15 kilonewton, minus 15 kilonewtons. This means that BY is equal to 15 kilonewtons acting down, or the opposite direction than which we've solved it. The internal force at that joint B is acting down. We can also, by knowing BY, we can directly solve for RAY, which was one of the problems that we wanted to solve, one of the main problems, one of our reactions. So sum of forces in Y is equal to 0, and we can say that RAY plus BY, as we've drawn it, they're both going up, is equal to 0. Now if we plug in our values, we have RAY plus minus 15 is equal to 0, so this gives us RAY is equal to plus 15 kilonewtons. So it's 15 kilonewtons acting up. I suppose we can put a little arrow there indicating which way it's going. And we can also apply our third and final equilibrium condition here. The sum of forces in X is equal to 0. And this gives us RAX plus BX is equal to 0. But we can't go any further than that with that particular equation. So we'll have to go and look at the other side of the problem, member BC. And this member BC we'll draw a free body diagram for, and we could say that it goes down 1, 2, 3, for every 4 it goes over. So member BC is here. It goes down 3 meters, and it has a horizontal length of 4 meters. And that means that its entire length itself is 5 meters. And if we put in our joint numbers here, or this is joint B, this is joint C, we said that already BY was acting downwards on member AB. We calculated it as 15 kilonewtons acting down. That means that it's acting up on member C, or BC. So we have a force BY is equal to 15 kilonewtons acting up. And we have an unknown force of Bx here. So we haven't calculated that yet. Bx, and we have a force C or Cy. I suppose we called this something different before. We called this force RCy, reaction Cy, and a force RCx. So with that free body diagram finished, we can see that we have three unknowns and three equations of equilibrium, so we can solve for everything here. Let's go ahead and attempt to do that. First, to do that, we can take the, well, first of all, we can realize that this is what we call a two-force member. And a two-force member behaves like a truss member. It means that it has constant force distribution over its length. There is nothing happening in between joints B and C. So the force in X at joint B has to be the same force in X at joint C and anywhere else along there. And the force in Y at joint B has to be the same force in Y at joint C anywhere. This means that By is equal to RCy. And, well, I suppose the negative of it. And Bx is equal to the negative of Rbx. And we already know one value, so we can say that, or sorry, RCx here. We can say that RCx is equal to, excuse me, we can say that RCy is equal to minus 15 kilonewtons. This means that RCy is equal to 15 kilonewtons acting down. And that's because of this equation here, By is equal to RCy. So we know that because it's a two-force member. Alternately, we could take the sum of forces in Y is equal to 0, and we would see that By has to equal to minus RCy. Now, we can take the sum of moments about a point to solve for one of our missing values in X. So if we take the sum of moments about location C, in this case, set that equal to 0, we can see that we have minus Bx times 3 meters. It's minus because it's rotating it in a clockwise direction, plus 15 times 4 meters, our moment arm, for the By value, and it's positive because it's rotating it in a counterclockwise direction, is equal to 0. And we can solve for Bx is equal to plus 20 kilonewtons going in the direction that we drew it. And this will give us the value of RCx immediately. So now, using the above equation, we can say that RCx is equal to minus Bx is equal to minus 20 kilonewtons. Therefore, RCx is equal to 20 kilonewtons acting to the left. So at this point, we can go back to the other side of the cut. We could go back to the member AB and determine the missing force, Rax, using our known value Bx there. Or alternately, we could take global equilibrium at this point because we have solved for 3 of our unknowns and we only have 1 missing, so we could solve for our unknown X force, Rax, with global equilibrium. Either way works just as well. So we'll go back to member AB to do this. We'll say that if we go back to member AB, and we'll redraw our free body diagram, and this time when we draw it, we're going to update it with our known values and be able to directly solve for our AX because of we're only missing one particular item. Oh, that's a pretty poor line. Alright, so we have a moment of 60 kilonewton meters. We have some known and unknown values. We solved for RAY already. So RAY is equal to 15 kilonewtons. We solve for our the internal force at B, BY. BY is equal to 15 kilonewtons acting down. We did solve for BX just on the previous page, and we solved for that by looking at the other member. So BX is acting equal and opposite to the other member's direction. BX is equal to 20 kilonewtons acting to the left. So we'll see with this other member here, we solved for BX, and we found that BX was acting to the right on member BC. That means that member AB is pushing on member BC to the right. The equal and opposite effect of that would have member BC pushing to the left on member AB at joint B. So BX, equal and opposite to this, is acting to the left of 20 kilonewtons. And then finally we have our unknown value of RAX. And so we could place we might as well put our dimensions here. 2 meters. And we could say that the sum of forces in X is equal to 0. This gives us RAX minus 20 is equal to 0. And this means that RAX is equal to 20 kilonewtons acting to the right. So at this point we've solved for all of the reactions as we were asked to do, and we're ready to draw the summary diagram. And the summary diagram should contain the information that we solved for. But we're going to put the diagram, or we're going to put the member back together at joint B. So we're not going to retain the internal forces at joint B in our summary diagram. We'll put that joint back together where we cut it before. Alright, so here's joint B, and if it's placed back together, the internal forces cancel out. We know we have a 60 kilonewton meter moment in the middle, and we have some reaction forces. We have a reaction force acting up and a reaction force acting down at the support. So we have RAY is equal to 15 kilonewtons, and our RCY is equal to 15 kilonewtons acting down. We have horizontal reaction forces. We found that RAX was acting to the right at 20 kilonewtons, and our CX was acting to the left at 20 kilonewtons. And these are joints C, A, and B. And our final step in our summary diagram would be to include our dimensions. 3 meters and 2 2 meters, and 2 meters. So at that point, we finished the problem. We found the reactions at A and B, and we did that by taking the section cut at, or reactions at A and C, and taking the section cut at joint B, placing both sides of the section cut in equilibrium, so member AB and member BC, and solving for the unknowns that we could on either side, and then going back and forth between these two members and updating them as we went. So it's a pretty systematic process to get the final results. And then we completed the project with drawing a summary diagram that contains all of the relevant information for this particular problem.